Good morning, guys. So we'll start today's class. Yesterday afternoon, we are supposed to have a class, but the network was very unstable, so I had to cut in. No problem. We will do today. Anyway, we have chemistry study hour only in the afternoon, so we will try to compensate for the all the lost classes that we had. Yes, and one more thing, it's official regarding classes from Monday, offline classes. The thing is, after we finish our main syllabus only, we will be going for books. In that procedure, there is no thing. But yeah, again, they won't make it compulsory offline. But whoever is online, they will sort it out. Like, yeah, they can have offline classes also, or online classes also. So, like, it's up to you. Whatever you want to attend, you can attend. Mm, that is one thing. First test is on 27th. Yes, it's on Saturday only, morning and afternoon, like the regular first test. Don't worry, we'll finish the syllabus. Okay, I have sorted it out. We will finish the syllabus. I mean, I was meant regarding alkynes part because alkynes is not included, right? And there are some small chapters also, only boards related chapters. That and all. Once the first test is done, we will finish. And yeah, though in the March second week or third week, like when your seniors are writing their names and all, for you they'll have one pre-boards it seems. So based on that, we will plan how to prepare and all in the April month. So a lot of things will happen on Monday. So whatever the free time you have, not free time, but the proper concentration of names, like you'll get a proper time only in this week only. So just saying so that you'll be prepared. Okay. All right, so let's start today's class. In yesterday, we have started the chemical properties, and in that, the first thing we have seen is hydrohalogenation, addition of hydrogen and halo parts from halo acids, right? So we will try to see. Could you repeat what you said about the offline classes? You have to come school from first. Yes, they will intimate you. They'll let you know. Yes, from first there will be offline classes as well as online classes. So it's entirely up to you. It's not like 100% you have to come offline. There is nothing. Transportation and all you have to decide. Those details college will send a message to you. But yeah, offline classes will be starting from Monday. And about what we'll do means first we will try to finish the pending syllabus, whatever we have alkanes chapter and the other chapters. Then we will be starting the board's preparation, and they have even prepared the important questions list. So even they'll distribute it once the like they'll distribute the hard copy once the classes start. So that is one thing. Yesterday evening only we had the meeting. That's why I'm saying it pakka. Otherwise I would say as far as I know, but yeah, it's pakka. In yesterday we couldn't listen. Yeah, I'll repeat again. I'll repeat again. Don't worry. Whatever I gave you regarding yesterday's class, I'll repeat everything again. Just please make note. All right. Okay. I'll give break in between also. Like it's gonna be 1 hour 10 minutes. Like it's gonna be a long class, right? So I'll give you break in between, so you can have breakfast or something like that in 5 to 10 minutes, and you can come back. As of now, let's start. So in yesterday's class, we have started this chemical properties, and in the first one, we have seen addition of hydrogen and halogen to wherever the carbon-carbon double bond was there initially, and now it was based on whatever the product we are getting as a major product. It was entirely dependent on the type of reaction intermediate formed, which was a carbocation. And also, this is called as Markovnikov's rule. Like the alkene, when it is being subjected to reaction with hydrogen halide or halo acids, so the hydrogen part of this HX will add to that carbon of carbon-carbon double bond where there are more number of hydrogens, in a way giving us a stable carbocation. And not in every case we can apply. There are some exceptions also. So the important criteria we have to take it down when we are applying this Markovnikov's rule is the alkene has to be unsymmetrical, because if it is symmetrical, something like this, like butene, this is symmetrical, right? This is carbon-carbon double bond. You have like equivalent groups on either side of carbon-carbon double bond. So there is only one option for us upon hydrohalogenation, that is only 2-chlorobutane. Even if we shift the electrons over here, right, all the mechanism, both the ways we end up with only one product. Whereas when we have unsymmetrical alkenes in the sense around this carbon-carbon double bond, the type of substituents are different. In that scenario, it will give us two different possibilities. Based on that possibilities, we have to add hydrogen. In such a way, we will get a stable carbocation. Or simply, according to the Marconi-Kobs rule, we have to add hydrogen H plus to the carbon having more number of hydrogens in the carbon-carbon double bond. So that is Marconi-Kobs rule. So that will be our major product. And one more thing, important thing is, whatever the substituents we are discussing on this carbon-carbon double bond or along the chain, alkene, proper alkene with a substituent, if we have, need not to be on carbon-carbon double bond. Substituents in alkene, it has to be an alkene. They have to be plus I groups only. Why? Because to this carbon-carbon double bond, in the end of the day, they are ending up with positive charge and negative charge, right? Mostly, we will be having the reaction intermediate where the carbon is having a positive charge. And what do we know regarding carbocation stability? Carbocation stability is directly proportional to plus I groups. So the more we have plus I groups, the more possibility or the tendency they will be following this Marconi-Kobs rule. So these are the two important criteria. The main reason, like you should have it out, aren't we getting a carbon-carbon double bond from carbon-carbon double bond? Aren't we getting both carbon with a positive charge and carbon with a negative charge? So why are we only discussing about the carbocation stability? The thing is, whatever the rate determining step we have written in mechanism and all, the first step itself is compromising this negative charge on carbon by adding a H plus, giving us carbon with a positive charge, CH, something like this. So we are getting a carbocation. That's the reason why we will be requiring plus I groups to further stabilize this carbon with a positive charge. And here, what is the type of group that is being added according to the electromeric effect? Obviously, the shifting of pi electrons after this is done, the type of reagent that is added will determine whether it is a plus or minus, plus C or minus C. Accordingly, this part of the mechanism, is it plus C or minus E, where a positively charged and electrophile is added onto the carbon after the shifting of this pi electron. Will we, where, how do we categorize it? Is it plus E or minus E? This part of the reaction.
Plus C.
Yes, very good. It's going to be plus E. Why? Because after the shifting of electron pair, that is pi electron, the type of group that we are adding will determine what is the type of electromeric effect. Okay, so one that is plus E in the plus C effect, that is positive electromeric effect. And one more thing, whatever this addition is happening, everything is electrophilic addition. So we can just make a note somewhere. This reaction is this addition reaction, because for alkenes, addition reactions are their characteristic reaction, right? So this is an electrophilic addition. Electrophilic addition reaction. Why? Because in the rate determining step, hydrogen with a positive charge, which is an electrophile, we are adding electrophile in the rate determining step. The first reagent that is added to this alkene is H plus, which is an electrophile. That's the reason why we are calling this as electrophilic addition reaction. How are we able to do it? Because alkene has become electron rich, it has formed a state where there is a lone pair, which means it has rearranged itself to become electron rich, which is a nucleophile. So obviously, an electrophile can attack at that electron rich center. So that's why this is an electrophilic addition reaction. That's why this reaction, addition of haloacids or hydrogen halide is an electrophilic addition, because in the first step we are adding H plus, which is an electrophile. So literally electrophile, addition of an electron deficient group or atom to the alkene is an electrophilic addition reaction. So two important criteria we have taken down. First thing is it has to be an unsymmetrical alkenes, because then only we have two possible products. Of them, according to the Markovnikov's rule, we can determine the major product. Second thing is, whatever the reaction intermediate we are having, it's a carbocation. So whatever the groups on this alkene, they should back up the stability of that carbocation. So these two are the important criteria if we want to apply the Markovnikov's rule. So this reaction is important for 2 marks in boards, or else in exams also they'll directly give you the alkene on bromination, sorry, on hydrobromination or on addition of hydrochloric acid. What will be the product? So you have to follow this method, Markovnikov's rule. You have to follow. So here you should get a doubt. Why exactly we are having plus I group? What happens if there is minus I group? Because also inductive effect, it depends, right? Type on depends on the type of products. Sorry, groups attached to the carbon-carbon double bond. Obviously, if there are plus I groups, there should be minus I groups. So, what is the scenario if we have minus I groups? So, this will that in that case that will be entirely opposite. So that will be our class today. That is anti-Markovnikov's rule. So take that down. So we will be having anti-Markovnikov's rule. So in this anti-Markovnikov's rule, exact opposite statement we are going to take. So how did we define this Markovnikov's rule in the first case? Addition of hydrogen as H plus to the carbon containing more number of hydrogens. So in anti means exact opposite. The addition of hydrogen takes place to the carbon with less number of hydrogen. But again, there are two cases for this Markovnikov's rule. Case 1 we will see, and after that case 2 also I will let you know. Case 1 will be related to minus I groups. So if the alkene has powerful electron withdrawing groups, if the alkene has powerful electron withdrawing groups, that is minus I groups, attached directly to the double bond, attached directly to the double bond, then the H plus of halo acid, then the H plus of HX, because that's the reaction rate addition of halo acid. H plus is added to the carbon, bearing less number of hydrogens, So this is an anti-Markovnikov's rule. So in this anti-Markovnikov's rule, if you have a strong electron withdrawing groups, then the major product will be opposite of the previous case, where the H plus will be added to the carbon containing less number of hydrogens attached to it. So let's take a small example, and from there we will see. So what do we have? CH2 double bond CHO on adding HCl. So there are two possibilities, because H plus and Cl minus. For this carbon-carbon double bond, the electron cloud can shift in any ways without considering this CHO in the first case, without considering this into the picture. You know, the carbon with the lone pair can be any one of these carbons. So let's write both the possibilities. Okay, and then we will see. So we have CH2, CHO. This is our skeletal structure, and we have CH2, CH, and CHO. So in the first case, according to the anti-Markovnikov's rule, what will happen according to this rule in discussion right now? The H plus will be added to the carbon containing less number of hydrogen, which means to the middle carbon. So it becomes CH2, and this part becomes Cl, and this will be the major product according to the anti-Markovnikov's rule. And according to the Markovnikov's rule, we have CH3 and Cl, and this will be the minor product. Just like in alkanes, how we have Sadzeff product and Hoffman product, here also we go with Markovnikov's product, Markovnikov's product, and anti-Markovnikov's product. I'm writing AMP, you write in full words. So when you have strong electron withdrawing groups in the alkene, then the opposite product, what you expect, will be the major product. Here, what's happening? We are supposed to get a stable carbocation. And what is the possibility here? Having a secondary carbocation. Like this is supposed to be our major product, but just because we have strong electron withdrawing group, and what does this electron withdrawing groups does? It withdraws the electrons from the chain, leaving a positive charge behind in the chain, and it itself ends up with a delta negative charge. So in the process, the electron cloud will be shifted onto this carbon, ending up with a negative charge. To that carbon we have our hydrogen going and adding. So this is just a statement. So you should understand the dynamics behind it, what exactly is happening over here. So if we write the both possibilities, CH2 double bond CH, CHO, in the first case of adding H plus without adding Cl, what do we have? CH3, CH plus, CHO, and in the second case, you have CH2, CH2, and CHO, right? So we are having a carbocation, and that carbocation is attached to an electron withdrawing group. So the electron density will be moving away from the carbocation, again increasing the net positive charge on the carbon with positive charge. And what is the relationship between carbocation stability and minus I groups? Carbocation stability is inversely proportional to the minus I groups attached to it. So that's the reason why if you have minus I groups, tertiary will be less stable than secondary than primary. If you have plus I groups, tertiary carbocation is more stable than secondary greater than primary. So in here, this is a strong minus I group. This is also minus I group. And here we have secondary carbocation, and here we have primary carbocation. So what will happen? Which will be more stable, secondary or primary? Everything is here only. You have to tell which is going to be more stable and why. Secondary or primary? Guys, you have to answer.
Secondary.
Yes, it's going to be secondary. Think properly. It's not secondary. It's going to be primary. Why? Because even if you have the stability order, it is for plus I groups. Here we have the opposite, minus I groups. So we cannot go for secondary carbocation as the stable one. Why? Because the minus I group is directly attached to the secondary carbon with the positive charge. And here, this is our required order. So this will destabilize. So minus I groups will destabilize the secondary carbocation. That's the reason why this will be our stable. Primary carbocation will be more stable. Primary carbocation is more stable, reaction intermediate is more stable reaction intermediate and and gives the major product, that is 1 chloro, no sorry, you have 3 chloro propane 1 all, right. So this is the reason behind altering the major product and naming it as anti-Marconi-Cov's rule. Yes, 1 second, I'll scroll up. Yes. So this is anti-Marconi-Cov's rule. The main reason we are going against the already existing rules is the type of groups attached to carbon-carbon double bond will affect the stabilities once the reaction intermediate is formed. Here, our reaction intermediate is carbocation. So the minus I groups, plus I groups, how they are related to stability. That factors we will consider, and we came to the conclusion that primary is more stable than secondary than tertiary, and that's the reason why the major product will be due to primary carbocation when we have negative inductive groups in the alkene. All right, so I'll wait a minute, you take this down, and then we will go for the next one. Or else meantime, those who are done writing down, I'll give you an example. You please tell me what is the product, major product that you'll expect. So what is the major product for this one? In presence of HCl only. It's 1 chloro-nitrobutane. Why? Because according to anti-Marconi-Cov's rule, the hydrogen attaches to the carbon with less number of hydrogen, which is the second position, which means chlorine goes to the first position. So 1 chloro, 1 nitrobutane, or 1 chloro-nitrobutane. Yes, very good. Because here we have minus I groups, right? Minus I groups. So what do we have after the addition of hydrogen? This will be secondary and this will be primary. So according to the minus I effect on the carbocation stability, plus primary will be more stable. So to this stable carbocation, our halogen will go and gets itself added. So CH2, CH2, CH2NO2, Cl. This will be the major product, and you do have another one, but that will be the minor product. CH3, CH2, CHCl, CH2NO2. Once can repeat regarding the minus I order and plus I order. Yes, ma, I'll repeat. You want me to show the intermediate step? Yes, 1 second. Uh, yes, I'll do both. Give me a second. Let me finish this intermediate and then I'll go back to the previous explanation. So in the first, there are two possibilities. Like after the H plus is being added, the first thing is if it gets added to the secondary carbon. So you have CH2, CH2 plus and NO2. 1, 2, 3, 4. Wait a second. Yeah, CH. This is not CH2. 1, 2, 3, 4. CH. And the another case when it gets added to the other carbon. So I mean the tertiary carbon to primary carbon to secondary carbon. So you have CH3, CH2, CH plus, CH2, NO2. So to this directly the nitrogen is attached. It further decreases the electron density. Wait a second. Both of them are having equal number of hydrogens, right? No, we cannot apply this actually. Both of them will give the same number of carbons are there. We have to go with the type of carbocation here. All right. So we cannot apply the H part, but we can go with the stable carbocation. So here minus I effect is maximum because of the distance. Here minus I effect is minimum comparatively. Oh, correct. Your answer is correct. 2 chloro we should get because of the distance factor. Minus I group is one carbon away. This is immediately attached to this carbon. Correct, correct. Minimum. So this will be the stable, and you have this as the major product. Correct, Nama. It's not one chloro because we have the same number of hydrogens to both the carbons. It's both of them are having one hydrogen only. So only thing we can judge is depending upon the number of the distance from which this I group is situated. Correct, correct. Correct. Minus I, larger distance, stable one. Correct. Okay. So this is anterior molecule. And please note down the minus I groups that you commonly come across. Mostly they'll go with nitro minus I group. They'll ask in these questions is nitro groups, cyanide, and then we have aldehyde as usual, and then we have alkoxide. No. COR and carboxylic acid, COOH. Okay, these are the minus I groups commonly encountered in these alkenes. All right. Yes, you are asking about the stabilities of these plus carbocations depending on plus I and minus I, right? So when it comes to the plus I groups attached, they are electron donating groups. In a way, while they are donating the electrons, they themselves are ending up with a positive charge. So whatever the positive charge is there, it is evenly distributed throughout the molecule whenever you have plus I groups. That's the reason why tertiary means attached to three other alkyl groups will be more stable than secondary, more stable than primary. Whereas when you have minus I group, they are further decreasing the electron density on the carbon with positive charge, increasing again more electron, creating more electron deficiency. So that's why they will destabilize. More the minus I groups you have on the carbon with positive charge, less is the stability. That's why tertiary will be least stable than secondary than primary. And here there are same number of hydrogens. So how are we deciding the major product is 2 chloro one thing means by on adding H plus the type of carbocation we are ending up and what is the distance of the minus I group from that carbon with the positive charge, because inductive effect is inversely proportional to the distance. So considering that factor, we have came with this conclusion. Right, I wrote as 2, that's why you got confused. It's supposed to be CHNO2 only. Okay, so this is anti-Markovnikov's rule when you have minus I group. There is also one special scenario, an important scenario. They have asked this question previous year mains, not recently, like some very old. This is very old question, but they did ask once. That is in case of peroxide. This is called as peroxide effect or Karash effect. Take that down as case 2 under anti-Markovnikov's rule. So we have Karash effect, SCH. Karash effect or peroxide effect. So the type of reagent we are using to perform this reaction will be entirely different and the mechanism will be different. So ma'am, they asked Antony Markov's rule in the yesterday. Markovnikov's rule in the yesterday's mains. First shift or morning shift? Actually, I didn't get through the papers actually. I did not get the papers. Did they ask? Then good. If you have the question, you can tell. Okay, I'll make a note. I didn't get the question paper. That's what. Hmm. Yeah, morning shift paper I have seen. Like 2 to 3 questions were asked from this GOC part. One was addition of HI to alkene, and one more thing was there. I forgot. Yeah, 2 to 3 questions were easy actually. Like the paper was easy, like it was easy to score. Even the physical part of the question, chemical equilibrium they have asked. Very simple question. Molarity problem they have asked. Like those are very easy questions, right? So like from chemical equilibrium part, they have asked very simple one. Wait a minute. I have question paper morning shift, afternoon shift I don't have. We will discuss in the afternoon study, Arma. That they are interesting questions actually. Okay, so please take down the next scenario where Antony Markovnikov's product is the major product. Okay, so it is specifically for HBr. So this was asked in the previous year mains. Why only HBr will give Antony will follow Antony Markov's rule, or why other halo acids will not follow? In that sentence, they have asked the question. So please take down this Karash effect or peroxide effect. So the statement is addition of HBr, addition of HBr to unsymmetrical alkenes, to unsymmetrical alkenes in presence of organic peroxides, organic peroxides, organic peroxides, that is benzoyl peroxides, C6H5COO taken twice, that is benzoyl peroxide, benzoyl peroxide gives anti Markovnikov's product, gives Antony Markovnikov's product as the major product, or it just simply follows anti-Markovnikov's rule. So why exactly we are seeing this means HBr, no, not HBV, it's R, HBr, hydrogen bromide. It's HBr. This reaction is specific for hydrobromination, not for hydrogen chloride, nothing. Only HBr will follow this reaction. High addition of HBr will follow peroxide effect in presence of benzoyl peroxide. Okay, so take any unsymmetrical alkene. The first unsymmetrical alkene will be propene, CH3 CH double bond CH2, and we are adding HBr. So if there is no peroxide, means we are just performing normal addition reaction. If there is no peroxide, what is the major product? According to the Markovnikov's rule, hydrogen has to attach to the carbon having more number of carbons, right? So if hydrogen is added to carbon with more number of hydrogens, what will be our product? We have CH3, CH, CH3, and here you have Br, 2 bromo propane. Now, in presence of peroxide, not only benzoyl peroxide, the regular hydrogen peroxide can also be indicated on the arrow. Even it will follow the same kind of mechanism. I will show you the mechanism also. So the thing is, when it is peroxide, then the reaction will follow anti-Markovnikov's rule, where the hydrogen of this will get itself attached to carbon with less number of hydrogen. So we have CH3, CH2, CH2, and what is left? The final terminal carbon only. To that, the bromine will get added. So we have 1 bromo propane. So in the previous case, in order to explain anti-Markovnikov's rule, we have used minus I groups as the basis to compare the stabilities. So what is the basis for this reaction then? We cannot just simply give the statement, right? We have to justify how come the major product is this one. Yeah, how come in presence of peroxide, the major product is this one. So this can be explained by free radical mechanism. Free radical mechanism. So whatever this addition is happening in presence of peroxide will follow free radical mechanism. So free radicals in the sense there will be an odd electron or unpaired electron on the particular reagent. And here the chain initiator will be bromine free radical. Why I am mentioning this bromine free radical means this will change the entire outlook while comparing the stabilities for the reaction intermediate. So let's see how this will proceed. So whenever we have any free radical mechanism, obviously there will be 3 steps. One will be chain initiation step, chain propagation step, and finally you have chain termination step. So in the chain initiation, free radical will be generated. And what did we tell? Initiator. What did we made a note? Initiator, that bromine free radical has to be produced. So that will be taken care by the benzoyl peroxide. C6H5, C double bond O, O, C double bond O, C6H5, because benzoyl peroxide is C6H5 taken, COO taken twice. So this will be our benzoyl peroxide. So what is the type of fission? Is it cleavage? Is it going to be homolytic or heterolytic cleavage to get a free radical? So we will indicate homolytic fission, something like this. Will we get a cation anion or obviously it is free radical? Achha, I only told the answer, no problem. So we have homolytic fission giving C double bond O, O, benzoyl free radicals. So 2 of them we will get. In the next step, this will further undergo homolytic cleavage. So this C6H5, C double bond O, oxygen with the free radical. This is the free radical. So homolytic cleavage between the phenyl group and the COO group. It will give us C6H5, phenyl free radical, and CO2 will be lost. Phenyl free radical. This phenyl free radical goes and attacks our HBr, C6H5. Here also homolytic fission or homolytic cleavage. We have C6H6, and here we got the bromine free radical. This bromine free radical will be the one attacking our reactant. Our reactant is propene. So what are the steps involved in the chain initiation? The peroxide, whatever the organic peroxide that we are using, that is benzoyl peroxide, will undergo homolytic cleavage, giving us phenyl free radical as the final free radical from itself. Like at the end of the day, after losing CO2, it gives phenyl free radical. This will goes and attacks our reagent, that is HBr, giving us our chain initiator, that is bromine free radical. So what is happening? The peroxide, in presence of peroxide only, we are able to get the bromine free radical, which is our chain initiator. So the entire reaction is dependent upon the cleavage of this homolytic cleavage of this hydrogen bromide or HBr, because of this phenyl free radical. So this entirely depends on the bond enthalpy, that is holding this hydrogen and Br together. Why I am giving this much explanation means, this is the a question they have asked in the mains. Why only HBr shows, other HCl, HF, HI, why they won't show this particular peroxide effect? So the main reason is, when this peroxide is attacking this bromine, this HBr, the HBr bond is broken down. So when we take HF, HCl, HBr, and HI, these two have very high bond dissociation energy. So they are more endothermic reaction, because they are comparatively having greater electronegativities, right? So the bond breakage requires more energy. And when it comes to HI, it is HI bond is very weak, very weak. Iodine free radicals will be easily produced, but the only drawback is they will react themselves and convert into I2 molecules. So that's the reason why this peroxide effect or Karash effect is seen only in HBr. This is the question they have asked. Why this peroxide effect is not seen in HCl and HI? Why? Because one or the other reactions involved are endothermic in both HCl and HI. The peroxide ion, whatever the phenyl free radical it is going to generate, that is not capable to break the hydrogen halogen bond. That's the reason why other hydrogen halides will not give this particular peroxide effect. Iodine will give, but the thing is, we cannot maintain these iodine free radicals stable. In order to do that, we have to maintain, we have to give, we have to perform some other reaction. So simply only HBr will show this particular peroxide effect or Karash effect. Why? Because the whatever the chain initiator we are using, the bromine free radical, it has to be generated by the cleavage of this HBr, which is done by the peroxide we are using. And that peroxide energy, like, it is not sufficient to break other bonds. Why HF and HCl do not show? Yes, you know that when it comes to the acidic strength, when it comes to acidic strength, HF bond between HF, HCl, HBr, and HI, HI is a better acid. So HF cannot lose hydrogen easily than HBr than HI. Why? Because the bond dissociation enthalpy is greater for HI than it does for, sorry, is greater for HI, more bond dissociation energy. So in order to break this HF bond, we require external energy. That is, this is an endothermic reaction. So if you see the reaction condition, we never mentioned about heating the reaction mixture. We are just performing this reaction in presence of a peroxide. The peroxide ion has to take care of generating the bromine free radical. So because HF and HCl are having greater electronegativity, their bond, HF bond, will be greater. So this peroxide ion, whatever the energy it is, sorry, this phenyl free radical whichever is generated from the peroxide, do not have that much of energy to break HF and also HCl. That's the reason why they won't show this particular peroxide effect or Karash effect. Okay. Let me see what's your doubt. uh, why only HBr? Yeah, that part I'm repeating again. Because the bond dissociation enthalpy for HF and HCl is greater, the peroxide will not be able to produce their halide free radicals because more energy is required to produce corresponding halide free radicals. When it comes to HBr and HI, they can be done, but HI, whatever the free radicals they are produced, that is iodine free radicals, they will combine and form I2 molecules, leading to no, what is that? Yeah, these iodine free radicals will not be there for the reaction to proceed further. Okay, that's the reason why HF and HCl, they are more of endothermic reaction. They require more energy to break, which is not provided by the peroxide. That's why they won't show. Whereas HBr, it can be easily broken down in presence of peroxide, so the reaction will carry forward. So this is about chain initiation. So everything is about producing the bromine free radicals. Yes. Yeah. Once again, yes. When it comes to HI, obviously the bond enthalpy will be less. So iodine free radicals will be produced easily, but they are very reactive. They cannot very reactive, and because of that, they will form I2 molecule. If there is no chain initiator, there is no point of discussing its addition, right? Because all the iodine free radicals will be consumed and be producing I2 molecules, right? That's why HI will not show, and HF and HCl also will not go. In C6H5 free radicals will have resonance. Yes, they will have extended conjugation. They will have, but they end of the day, if they are free radicals, they are electron deficient, right? So they will seek for electron rich center, which is provided, like not electron rich, but they will seek to pair up that unpaired electron. So that's why they will attack the HBr. So if we say we have that C6H5 free radical doesn't have enough energy to break HCl and HS bond, is it enough? Yes, it will be enough, or else you can say the chain initiation step for HF and HCl are endothermic reactions. They require some energy, some initiation, like some external energy should be provided. Yeah, you can say that part also. Like both the points are correct only. I will give you the exact question also. Don't worry. After this mechanism is done, I'll give. Okay, let me finish this mechanism. So the next step will be chain propagation. Chain propagation in the sense our chain initiator goes and attacks our substrate. So what is our substrate? CH3, CH double bond, CH2. So we are, yeah, this bromine free radical goes and attacks our propene. Now there are two possibilities again. Whatever the pi bond is there, that will also undergo homolytic cleavage, giving us again two centers with unpaired electron. So in the first scenario, what do we have? Let's say this is carbon number 1 and this is carbon number 2. If the bromine goes and attaches to the carbon number 1, the bromine free radical, we have CH3, CH, CH2, Br. So in the second case, if the bromine goes and itself attached to the carbon number 2. So CH3, CH2, CH2 free radical. So here you have bromine, right? So this is secondary free radical and this is primary free radical. Yes or no? So what will be the stable one? Is it going to be primary or secondary? Free radicals. After this attack of Br is done, all right. So which is going to be a stable free radical? Is it primary or secondary? Is our free radicals electron rich or electron deficient? Which is going to be stable one? No. Secondary will be more stable because it will be backed up. Like it's just like carbocation. Free radicals are electron deficient. So if the electron deficiency is distributed throughout the molecule, just like positive charge is distributed in carbocation, they will become more stable because of the charge distribution. Here also the same explanation. Carbocations and carbon free radicals are electron deficient and they follow the same order. That's the reason why we have secondary carbon free radical, carbon free radical as the stable intermediate. And that's the reason why the substitution, the next part will give us the major product. So we have 1 bromopropane. So one second. That's the reason why in presence of peroxide we have 1 bromopropane as the uh, major product. So what do we have once this free radical is formed? So in presence of H plus we will have CH3, CH double bond CH2. So this will be our major. This will be our major product because this will be the stable free radical. What happened? Will distance from Br affect free radical? Bromine is a bigger ion, right? It has a less electronegativity. So fluorine and chlorine, if they are present, probably they would have affected. But the thing is here, first thing, bromine is less electronegative compared to the rest of the halogen. So we can ignore the minus I effect coming from the bromine. So even if you are talking about the distance factor, both of them are at equidistant. So whatever the I effect the bromine offers, whatever the least it is offering, even that will be inconsiderate because it's equal in both of the carbon free radicals. So we will go with the regular order, that is tertiary more stable than secondary than primary. So the secondary free radical will be the most stable uh, carbon free radical, giving us our major product. So what will happen here? We got our alkyl free radical, right? Now this will goes and attacks. This will goes and attacks our next one. Wait a second. So this is part one of the propagation, and the second one will be the secondary free radical, whatever it is produced. Secondary carbon free radical abstracts hydrogen free radical from HBr to complete addition. Indirectly we are regenerating the bromine free radicals we had. So what do we have? CH3, CH, CH2Br. It is going to attack our HBr, homolytic fission, and this will get goes and attacks over here. So we have CH3, CH2, CH2Br, and the bromine free radical will be regenerated. Could you please repeat propagation? You did not understand. Yes. So when it comes to propagation part, the chain initiator will attack the alkene. Now, once it has attacked the alkene, it will give us carbon free radicals only. Why? Because it is a free radical. Obviously, at the attacking site also, there has to be homolytic cleavage only. Now, if this bromine attacks on the carbon number 1, we have secondary free radical. If this same bromine free radical attacks on the carbon number 2, we have primary free radical. Now, between these two, we have to compare the stabilities because the stable reaction intermediate will give us the major product. So, between secondary and primary, carbon free radicals, both are electron deficient only. We just have to compare the stabilities in which free radical there is efficient distribution of electron deficiency throughout the molecule. So what do we have according to carbocation stabilities? the tertiary greater than secondary greater than primary. So here also the secondary carbon free radicals will be a better stable carbon free radical than primary. So this one will give us major product, that is 1-bromo propane, and the addition part is completed by this alkyl free radical attacking the HBr to give or to regenerate bromine, and our major product, that is 1-bromo propane. 1-bromo propane. Why we are concentrating on mechanism means we never know how they ask questions. But you should know, giving right away and understanding the statement is different, and how exactly you can rationalize, or how exactly you can justify that particular product as major product is important. That depends entirely on the reaction intermediate, what are formed, how they are formed, and what are the factors affecting their stability. Here we have free radicals regenerated, generated. That's why we are going in terms of stability of carbon free radicals, where secondary is more stable than primary, and this secondary free radical will be responsible for the major product. Okay, so clear, right? Propagation step. Still anyone having any doubts in this? I'll give you the termination step. Then you can have some 5 minutes break. After that, we will go to the next part. So please take down the chain termination step. These are going to be simple only. Whatever the intermediates are there, they will interact. So first thing is, if the initiator itself, if they are going to interact, we have Br2, then the reaction will stop, or else the alkyl free radicals. What is the alkyl free radical? Major one we have CH3, CH, CH2Br. If two of these will interact, or if this is going to interact with our chain initiator Br, we will be getting a molecule CH3, CHBr, sorry, yeah, bromine free radical. You have Br and CH2Br. So these are the two ways by which the reaction comes to an end. Either both the bromine free radicals have to interact, or one alkyl free radical and another bromine free radical. They'll just react and give us a substitute, an added product. Okay, so the main thing you have to remember is the conditions. What are the conditions? What factors you have to consider while determining the major product? First thing is, what is the intermediate, and the second thing is factors affecting the stability of intermediate. So these two factors we have to consider. Then only we will have a clarity on the final major product. So you guys can have a small break for 5 minutes. What's the time exactly? It's 9:01. So at 9:05 we will start the class again. I'll minimize the screen. Those who are still writing the above part, you can write. Okay. All three steps are there in one page. You can just take them down.